All right, so let's continue. All right, so this is where we were in the last lecture. We were looking at the inverter delay, and also we were noting the impact of variations, process variations, which result in KPN not having a definite value but lying within a range, and similarly, the threshold voltage is not a single value, but again it lies within the range. And on the basis of the values of KPN and VTHN, we can classify transistors as slow transistors. Slow meaning KPN is low, and VTHN KPN is at its lowest point, and VTHN is at its highest value, and that results in the lowest value of current, and that translates lowest value of current translates into the highest value of delay. So that's why we call such a transistor as a slow transistor. And another name for it is a weak transistor. Weak in the sense that the current is associated with it is small. And corresponding to that, we have a fast transistor where KPN is at its highest value, and VTHN is at lowest value here, so which results in the largest possible value of drain current and the smallest delay. So we call that transistor as a fast or a strong transistor. So we have these various possibilities. We have these transistors which we can call as typical transistors, typical or nominal values of transistors here. So a typical NMOS and a typical PMOS. Then we have a fast NMOS and a slow NMOS. And we have a fast PMOS and a slow PMOS here. And the consequences of this are, one is shown on the voltage transfer characteristics. The black curve here shows the when you have typical values of threshold voltage at KPN. So that's the typical VTC here. And if we look at a fast PMOS and a slow NMOS, fast PMOS means this is a strong PMOS and a weak NMOS here. So remember, what NMOS does is it tries to maintain the output voltage to VDD. It provides a connection to VDD here. And when I have a fast or a strong PMOS, it tries to keep the output close to VDD for as long as it can. And that's why you can see here with respect to the original one, this stays, the whole characteristic then gets shifted to the right here. So a fast PMOS and a slow NMOS characteristics is shifted to the right. And the other extreme is a slow PMOS and a fast NMOS, and the characteristics is shifted towards the left here. So that's one immediate consequence on the voltage transfer characteristics. And characteristics shifting right or left eventually impact VIL and VIH. So this is for typical transistor. If we do the calculation, assuming that KPN can vary, this is a nominal value, 100 microamperes per volt square. If it can vary plus minus 20%, and P is 50 nominal value, it can also vary plus minus 20%. Threshold voltage, let's say, can vary plus minus 0.1, and similarly 0.1 here. So on that basis, we can calculate what would be a fast transistor. Fast NMOS would be, KPN would be 120, VTHN would be minus 0.9. So that would be a fast NMOS. And on that basis, we can, then find out what the KPN and KP values are for the slow and the fast. And one can calculate what is VIL and VIH. So for this case, a slow PMOS and a fast NMOS, the values are, we saw here, everything is shifted towards the left. So the values are VIL is 1.3 and VIH is 1.63. And a fast PMOS and a slow NMOS characteristics are shifted to the right. So VIL also goes to 1.67 and VIH is 2. So it's not fair to call noise margin as only by looking at the typical characteristics. If I have a typical NMOS, typical PMOS, VIL and VIH are here, it's not fair to say that this is the noise margin, because some of the NMOSs will have characteristics, some of the inverters will have characteristics like this, some of them will have characteristics like this. So what we should do is maybe look at the minimum, to define noise margin low, we should look at the minimum value of VIL that's possible, which in this case is 1.3. And to define the noise margin under high condition, we should look at the maximum value of VIH, which is 2 volt here. So effective noise margins then are 1.3. are only 1.3. 3.3 minus 2 will also give you 1.3 here. So effective noise margins are only 1.3. These are not 1.48 because in an actual circuit I will have variations. I'll have slow PMOS and fast NMOS and all those variations that will be there here. So one of the consequences of variations that you immediately see is that the noise margin reduces. If I didn't have variation, if all the transistors had the same KPN, VTHN and all that, I would have had 1.48. But because of the variations, now I have 1.3. So that's one consequence. The other one, of course, is impact on delay. Now, delay, let's look at, besides the process variations, slow and fast and MOS, we also have temperature varying between 0 and 125 degrees. And supply voltage can also change. Typically, we take plus minus 10% variation in supply voltage. And process variations, of course, are here. So we can have delay lying, for a simple inverter that we looked at, lying in a variety of places because of these variations here. Now we can draw this particular diagram here, which shows, which helps us to calculate the best and the worst case delay values here. So these show all the, along this axis I have temperature, showing that temperature can vary between 0 and 125. On this axis is the supply voltage. Plus minus 10% means supply voltage can vary between 3 and 3.6. In between I have 3.3 here. And process variations are there. Process variations are here. So we have written is a fast transistor or a slow transistor and things like that. Okay. And so you can see here that at this particular point is where I will have the minimum delay. At this point I will have the minimum delay here. At this point, because I have a fast process here, fast transistor. Let's say fast NMOS, if we are looking at tau P high to low, so NMOS is causing the, providing the current for discharge. So I have a fast transistor. I have supply voltage, which is 3.6. I have high supply voltage, so we have high current here. And I have temperature, which is 0 degrees. 0 degrees, which means mobilities are higher. And for that reason, again, I have a higher current here. So this corner here provides you with the maximum current. Temperature is low, the supply voltage is highest, and the transistors KPN and VTHN are such that the transistors it's a fast transistor here. So you get the minimum delay at this particular point. And then by the same logic, you get the maximum delay here. When the temperature is 125 degrees, when the supply voltage is minimum 3 volt, and when the process is, the transistor is slow. So you get the minimum delay here. And of course, we can see here delay can lie all over this particular, inside this particular cube. Delay can be anywhere inside. These are the corners at which, so this is the best case delay and this is the worst case delay here. So that's how at least these values are of interest to us, so that we know between what limits my delays lie. Worst case is obviously important because we've seen that in order to calculate the clock frequencies and all that, we need to identify the worst case path. And in the worst case path, we should obviously take worst case delay values also. Worst case delay values for all the inverters and the gates, so that under worst case condition, our IC works with that clock here. With some actual data here, so this is 180 nanometer technology that we were talking about. And the manufacturer provides the following information. If you look at this particular expression, so the manufacturer is telling the following, that let's say you have a typical delay. I already showed you earlier how the typical delay, whether it's low to high, high to low, and all those delay values that are there. Whatever is the typical delay, typical means for a typical NMOS or a typical inverter. What the manufacturer says is, to calculate delay under variations, what you should do is multiply it by these factors to arrive at delay values under variation. So one factor is process. Process could be a fast, resulting in a fast NMOS or a fast PMOS and all that. So one says there's a K process here. That's one thing. The other one is the effect of VDD change that you can see here. And the third one is the effect of temperature change. So what the manufacturer is saying is, if you want to, whenever the delay values that the manufacturer is giving, the manufacturer is giving the delay values at a nominal supply voltage for a nominal transistor and for a nominal temperature of 25 degrees Celsius. That's what the manufacturer is doing. And if you're interested in that some other supply voltage, some other temperature, You want to calculate worst case or best case and all that. So the manufacturer is suggesting use an expression like this. And it's providing values here. So let me show you. So it says for K process, for normal process is 1 by definition. Slow process, which means 1.293, which means multiply delay by K process, which is 1.293, which means 29.3% higher because of process variations. Fast process means he says multiplied by 0.781, which means about 22% faster. So multiply by 0.781. So these are the values that are based on measurements that the manufacturer is supplying. Slow process and a fast process here. So you have to multiply by these factors depending on what you are calculating. Then the manufacturer is providing this parameter multiplying proportionality factor K volt. K volt, remember, so as the supply voltage changes, you have to, K volt is there, the amount by which the supply voltage changes, and you get this factor here. And similarly, K temperature. Right? So if based on this information, if I want to calculate the best case delay, minimum delay, so tau p minimum divided by the nominal value, whatever is the nominal value, will be equal to 0.78. I use a fast process, 0.78 into 1.51 K volt. I use the highest supply voltage, which means that go up to 1.98. 1.98 minus 1.8 will give us 0.18 here. So that's where this factor is. And then I use the, go to 0 degrees here. 0 degrees here. So I use 0.001371 minus 25 degree lower here. So we get this factor here. So what we arrive at is tau p minimum by tau p 0 is 0.66. So actual delay value can fall as much as, you can see here, 32%. 32% below what the nominal value is. And similarly, I can calculate what is the maximum value here. By taking again a slow process and all that, I can calculate, it comes out to be 1.64 here. So it can be as high as 64% higher under these variations here. So a typical, whatever, let's say delay of a typical inverter may be, say 40 or 50 picosecond, it can fall down by this much and go up by this much here under these process, temperature and voltage variations. So that's something to be aware of, and these are obviously taken into account in when one is deciding the clock frequencies and other things that are there. All right, coming again, what is the easiest way of decreasing delay? Well, as we just saw, easiest way of decreasing delay is that you increase the supply voltage. Given an inverter, why am I saying is the easiest? Because look at the inverter. What is it that you can change in an inverter? You can change in an inverter what is the supply voltage at which you run the inverter. And the next thing is, what are the sizes of the inverters? Sizes of the inverters changing is, I mean, once you fabricate, obviously you can't do it. But otherwise also, it requires more effort. Very simple way of changing delay is just increase the supply voltage. So for example, for the inverter that we were looking at 3.3, it had a tau PHL of 75 picosecond. When I go to 3.6, note that what is happening is supply voltage is increasing here, but the current increases faster than the linear variation in voltage here. So current increases faster than this simple thing. And so 3.6 gives us 65.5. It's a straightforward calculation of current. 4 gives us 54.8. 5 gives us 36.6. So very easy to reduce the delay. Any IC that you want to drive it a little bit faster, apply a higher supply voltage here. But note also the consequence. The dynamic power dissipation was the node capacitance here, VDD square into F. So if normally the dynamic power dissipation is described in terms of how many watts per, let's say, megahertz here. So dynamic power dissipation here is 0.22 microwatts per megahertz. Dynamic power dissipation is 0.5 microwatts per megahertz. So that's the price that you're paying. If you increase the supply voltage, well, you're decreasing the delay, but the power dissipation, as you can see here, if you've made the delay half, the power dissipation is also gone. Doubled here. So that's one of the prices that you pay. The other thing, of course, is when a manufacturer is saying the optimum supply voltage is 3.3, and you run it at a higher voltage here, there is of course a safe limit within which you can run. But in general, if you drive it at higher, as you can see, higher power dissipation, there may be issues of reliability and other things also. You will end up dissipating more heat and there may be problems. The other one, a harder way of changing the delay is by changing the size. By changing the size of the inverter. And we said that if you look at an expression for delay, there's an intrinsic part and there's an extrinsic part. The intrinsic part to the first order approximation doesn't change that much with the size here, but the extrinsic part, the inverter has to drive a load capacitance here, and this factor A is directly proportional to the size. So if there is a capacitance, heavy capacitance or whatever is attached to the inverter, and that's contributing a lot to the overall delay, well, you can increase the size of the inverter. Increase the size of, and when you increase the size of the inverter, increase the size of both the NMOS and the PMOS proportionately. If you don't increase it proportionately, then two things happen. Your voltage transfer characteristics then tend to become asymmetrical and noise margins start getting compromised. And if you don't increase Wn and Wp in the same manner, the delay values will also become asymmetrical. So, if I simply increase Wn, tau PHL will, let's say, improve, but tau P LH will not improve. So as I increase Wn, I will have to increase Wp also to balance. So in this case, it helps, as I said, if this is a significant component of delay, extrinsic delay, increasing the size of the transistor will cause a reduction in this particular term. A will be inversely proportional to Wn, not directly proportional. Inversely proportional. So as you increase the size of the NMOS, the delay value will decrease. And as I said, first order approximation, the intrinsic values will remain the same. But there's a problem with it. Focusing on this inverter, increasing its size will reduce the delay. But then the other thing which is important is the input capacitance here. The input capacitance of A, which is proportional to the size of the NMOS and the PMOS. So the input capacitance then will also rise. So as you're able to reduce the delay of this inverter, this particular capacitance increases, and whichever is the previous gate, its delay will tend to increase. Because you're causing more loading of the previous stage. You're increasing the capacitance at A by increasing the size. So you cause a loading of the previous stage. So yes, you're able to reduce this inverter, but you have increased the delay of the previous stage here. And you have to balance. You have to make sure that the amount by which you reduce here is more than the amount by which you increase the delay of the previous stage. So you have to do a balancing act. You're never looking at one inverter in isolation. Okay, so we'll look at the sizing issues, because you can't size an inverter in this case in isolation. You have to look at the previous case also. So if you're wondering what is an ideal size of an inverter, well, that depends on the environment of the inverter. What is connected to the output of the inverter and what is prior to the inverter. And according to that, we'll decide whether we are going to use a 1x inverter or a 2x or a 4x or a 16x or what kind of inverter we will use. So the environment will decide what kind of an inverter would be required here. All right, so that's as far as the delay is concerned. Power dissipation we've already looked at very quickly. Power dissipation has, in general, we've discussed two parts, static and dynamic. And in the dynamic part, we've added another one, which you will see in a minute why this is there. This is called the short circuit current, power dissipation due to a short circuit current that may happen here. All right, static power dissipation basically means that you have applied a stable zero, a static zero, and or a static one, and you're looking at how much is the power that is being dissipated. Now, if I apply a zero here, as you can well see, if I apply a zero here, which means ground here, PMOS is on, NMOS is off. And the same way, if I apply a VDD here, PMOS is off and NMOS is on. So one of the transistors is off. One of the transistors is off, so there is no encodes. There is no direct path. If I say off is an open circuit, then obviously there is no direct path from VDD to ground and no current is being taken from the supply. But it does turn out that even when I apply a ground here and I look at an NMOS, when I apply a ground here, this is obviously on, and note that the voltage at this particular point will be VDD. If this is on, the voltage here will be VDD, the voltage here is ground. I have a drain to source voltage here, and there are leakage currents that are flowing in the transistor. and the leakage currents in modern technologies have become significant. So that's why these things are in quotes. In the older technologies, if the transistor was off, we could say, well, no current is flowing, or almost negligible current is flowing. In modern technologies, we can no longer say, if the transistor is off, that there is a small current still flowing through the NMOS. So it would be limited by here. And it depends on, if time remains, we'll towards the end, we'll look at what are the sources of the leakage currents and their magnitudes and all that. As a first order approximation, this is again in quotes, we'll say this is a small power here. The off current is small. So it's not as significant as the next power here, which is the dynamic power. So dynamic power comes about because you are switching. As you're switching the input, the output capacitance charges and discharges. And we have seen this, that every time you charge a capacitance, you take an energy equal to CT VDD square from the supply. You store about half CT VDD square on the capacitor, but the other half of the energy is dissipated in this particular transistor here. And then so this is for charging. When you discharge it, that half CT VDD square also gets dissipated in this particular transistor here. So on an average, when I switch my input at a certain clock frequency, we get a dynamic power dissipation, which we had seen in detail, F times CT times VDD square here. So it's the same expression that we had seen earlier. This net capacitance, whenever it switches at a frequency F, and the voltage within a voltage to which it swings, 0 to VDD, results in a power dissipation here. So that's the dynamic power dissipation, which, as I said, calculated per megahertz. So it's 0.22 microwatts per megahertz for our example that we are looking at here. So that's the dynamic power dissipation. There's another power, I'll come back to that. There's another power that is dissipated. As I said, during static 0 and 1, there is no path from VDD to ground. But when you're switching, a path from VDD to ground does form. So look at this behavior here, especially when you're switching under input which has a rise time and fall time. So normally note that abrupt input and outputs are not a common phenomenon. Normally the input would be rising at a certain rise time, falling at a certain fall time. So this is a more realistic case here, although it won't be rising linearly and falling linearly like this. But this is a more realistic case where the input is going from 0 to VDD with a certain rise time, and then falls from VDD to 0 with a certain rise time. Now, if you look at, if I apply an input like this to my inverter, now when I'm at 0 here, it's clear that my PMOS is on and NMOS is off. And therefore, there is no path from VDD to ground. But the moment I cross the threshold voltage of the NMOS, if I cross the threshold voltage of the NMOS turns on. And at this point, the voltage is still low enough that the PMOS is also on. So PMOS is on, NMOS is on, and I have a direct path from here to here. Right? Note that the PMOS will turn off when the input at this particular point is VDD minus VTP. VTP threshold voltage here, so VDD minus VTP. So PMOS will turn off here, and NMOS is off here. So in between, both NMOSs and PMOSs are on, right? And both NMOSs and PMOSs are on. There is a path from VDD to ground, and that's what we call a, it's not really short circuit. Transistors have resistors, so we say it's as if there's a short circuit path from VDD to ground because both transistors are on. In simple terms, we say when the transistor is on, it's like a short circuit. When the transistor is off, it's an open circuit. But obviously, it's not like that. But you can see that a path from VDD to ground forms in this voltage range. At this point, the current is low because the NMOS is just turned on. So the current is really low and is limited by the NMOS. As the input increases, the current is still limited by NMOS, and so the current increases here. Current rises here. At this point, we can understand the PMOS is just at the edge of conduction, so the current is again 0 here. And if I'm closer to here, then the PMOS is a limiting factor for current here, and therefore, as I'm reducing voltage, the current decreases here. So somewhere you can see here, current rises here, reaches a peak, and then falls back to 0 here. So as a simple case, you can approximate it by a triangle here. It's not really a triangle, but you can approximate it by saying that it starts from a small value, reaches a peak, and then falls again to small value here. So this is why it happens here between these two limits. And similarly, whatever happens in these two limits will also happen here also when it's falling. So you get this here. So there's a power dissipation because of this. Every time you are switching an input from low to high, you're getting a current which is flowing in this from VDD to ground here. And every time you're switching here, a current is flowing here. So normally we model this as power dissipation as I said, it's a triangle. So you can take half, if peak value of the current is I peak, so the average value is half peak. And this is a fraction of the rise time, tau r. So it's not flowing for the entire rise time, but as I said, this is an approximate expression. The current is flowing only, the base part is not really the rise time, but a fraction of the rise time. And similarly, the base part of it is not really the fall time, but a fraction of the fall time here. But anyway, you can see here that an approximate expression is half I peak, tau r plus tau f. So that's the area of this particular one divided by T here times VDD. So that's the average power that is drawn once you switch in this particular manner. And if you, so what this is saying is that in an inverter, if the rise time and the fall time of the inverter increases, the power this contribution of the power dissipation also increases. And so in general, a fast rising and a fast falling inputs are desirable from a point of view here. If I estimate the peak current by looking at, by saying that the peak value occurs at VDD by 2, once it reaches here, the peak current is about what is given here. And if we calculate, the value comes out to be for tau r equal to tau f equal to 0.1 nanosecond, a small value here. It's not, it's there, but it's not as significant as the dynamic power dissipation that we calculated here. But anyway, for the sake of completeness, you should be aware that there is a direct path does form, and there is a short circuit power contribution also. So, but not as significant. You can see here 0.007 microwatts per megahertz here. This is also proportional to frequency as compared to the previous value, which was 0.22 microwatts per megahertz here. So this is more significant here. All right, how do we reduce power? Again, reduce the supply voltage. If the dominant power is here, dynamic power, reduce the supply voltage. And you can see here, reduce the supply voltage and reduce the capacitance. So reduce the supply voltage is obvious. Reduce the nodal capacitance, which means CT. So by if possible, choosing a smaller transistor sizes, by doing the layout in such a manner that you note that this CT has interconnect capacitance and all that. So you do layout in such a manner that the capacitance at this particular node turns out to be minimum possible here. So that's the other way of doing it. And the third way is reduce the switching activity of the nodes. In this case, switching activity, which means in the number of times this particular node switches in a particular time period. So, well, if it's being driven by an input like this, you don't have much control. But in many other cases, you'll find that by careful choice of how you design the circuit, you can minimize the switching activity. Switching activity meaning, again, number of transitions it makes from 0 to VDD and VDD to 0. So you can minimize the switching activity through design and reduce the power dissipation. Not in the case of inverter. Inverter is straightforward. You can't do much. But in other cases, you have some freedom. All right. So that's sort of a summary of the inverter that we have just looked at. All the important characteristics of an inverter are shown here. So each one of these things you should understand well, because this inverter forms the basis for all complicated gate design. So the principles that are used here are the same principle that are used in other gates as well. So as you can see here, the static characteristics are important, VTC, and how we the freedom that we have with respect to VTC is defined by this particular equation here. The ratio of the NMOS and the PMOS transistors defined by beta R. So through this beta R, we can shift the VTC to the right or to the left and thereby alter VIH, VIL, NMH, NML, and all that. And how VTC is affected by fast and slow and slow and fast, all those transistors here. So that's the VTC part here. This, of course, the area part here. The area of our inverter is here, 1120 lambda square. The layout also gives us the area of the drain, the perimeter of the drain, both NMOS and PMOS, which are needed for calculation of delays. And delays are understood through this equation. Delay is basically charging of the nodal capacitances to a value equal to 0.5 VDD. And what you have to next look at how much current is available for charging and discharging. So that's the key equation here. And delay can be broken into intrinsic and extrinsic parts here. And the delay is this only tells you about the delay under abrupt switching condition. When you abruptly switch input from low to high, high to low. This tells you that the delay values can be significantly larger when the input and the output, when the inputs have a rise and a fall time. And then you may use a simplified expression like this to estimate the delay under that condition. Note that this particular inverter, again, reminding you with abrupt switching gives you 75 picosecond of delay. This particular inverter, which is being driven by the previous inverter, so obviously there's a rise time and a fall time. This has 134 picosecond. So this is a important point to keep in mind. What we are estimating is through our simple expressions are this value here, 75. But then it has to be taken, and then maybe an expression like this can be used to estimate delay under rise time and fall time. All right, so that's as far as the inverter is concerned. Since we are running short on time, I would have spent more time on discussing. Maybe if time remains, we'll come back to the inverter, because the interesting thing happens after you collect all this information. That the next thing to ask is, what if I scale my inverter? What if why do I want to scale my inverter? Because scaling has been one of the defining characteristics of digital ICs, of the whole microelectronics scaling of MOS transistors. So if all these values that are given, I've given you for lambda equal to 0.3 or effectively 0.6 micron technology here. So if I scale lambda, let's say if I go from 0.5 or 0.6 micron technology to 0.35 or 0.25, you can immediately begin to see what effects will occur here. How the area will go down, how the drain area and the perimeter area will go down, what happens to the delay, what happens to the power. All those interesting things will begin to occur, with the information that we have. And a nice discussion can be as I go from 0.5 to 0.35 to 0.25, again to 0.18 to 0.13 to 90 to 45, and look at how the inverter performance changes. How this whole subject evolves. As I said, time remains. Maybe towards the end we'll come back to this. Right now, what we need to do is, having looked at inverters, we need to look at the basic gates. The first basic gate is our 2-input NAND gate here. So note that we are talking about a fully complementary CMOS technology. So whatever happens to the NMOS network, same thing happens in a complementary manner to the PMOS network. If you see two NMOSs with inputs A and B connected in series, you'll find two NMOSs, two PMOSs connected in parallel. It's a fully complementary technology. Easy for you to verify that this particular gate will perform the NAND operation. I need both A and B to be high to pull this particular node down. Otherwise, this node will always be high here. So you can see it performs a NAND operation. And the issue, so the structure of the NAND gate is fixed. The issue is what sizes. So that's the information, that's the freedom that the designer has. What size of PMOS should I choose here? And what size of NMOS should I choose here? All right. And for that, remember the sizes that you choose have an impact on these 4 parameters. Noise margins get affected by your sizes, delay will get affected, power will get affected, and obviously area will get affected. So when we evaluate a particular size for these devices, these are the 4 parameters that we have in mind: noise margin, delay, power, and area. Now, what size? So one cannot say, well, choose this particular size. As I've been saying, size, noise margin is local to a, let's say, local to a gate. It doesn't depend on, let's say, what happens in the previous gate or the output gate here. Let's say it's local. Delay of a gate it depends on what is connected to this particular gate here. Because note that delay comes about because of the capacitance. And the capacitance, some part of the capacitance will come from here, and some part of the capacitance will come from the load. So the delay is something that I cannot decide just by looking at a NAND gate and saying, this is the size that you should use for minimum delay. One cannot do that, because delay depends on, as I said, on the environment of the NAND gate here. The power dissipated in this particular NAND gate also depends on, as you can see here, on the net capacitance at this node, because it's the capacitance which is switching on and off. So the power depends partly on this and partly on the load. Now, if you want to minimize the power, obviously you'll like to minimize the net capacitance at this particular node here. And for that reason, you should try and use the minimum sizes of transistors so that the nodal capacitance here becomes small. Note that the delay, the intrinsic part of the delay to the first order approximation doesn't depend on the size. Because as you increase the size of the transistors, the capacitance increases, but the current also increases. And so capacitance by current sort of balances out, first order. But the power does depend on the size here. The capacitances depend on the size. And area, of course, we understand. But remember, area does not simply scale with, if I double the size of the NMOSs, doesn't mean the area doubles. All right, so it's not as simple as that. So one of the ways in which we can size a NAND gate is by remembering something about the inverter. Now, if you look at, this was our design for an inverter. Inverter, we took this as 4 lambda by 2 lambda. Why? Because this was the minimum size of the NMOS allowed. 2 lambda is the minimum length and 4 lambda is the minimum width for the technology that we are looking at. And we chose this 8 lambda by 2 lambda to balance the noise margin. To get a symmetrical VTC, we chose this to be 8 lambda by 2 lambda. And, you know, it balances the current of the PMOS and the NMOS. And we end up getting the same delay for the tau PHL, tau PLH, all those things that we get. Now, when we go towards a NAND gate, one of the things that we can do about the NAND gate is that we look at, that we should size this particular, let's say, PMOSs and NMOSs in such a way that the ability to drive a subsequent gate of the NAND gate here, you know, whatever capacitance is connected here, the ability to drive that particular capacitance, which means to charge that capacitance and discharge that capacitance of the NAND gate, is similar to the ability of this particular inverter. One of the starting things we can take here. Basically, which means what? Remember, we took this inverter and we took the load of this particular inverter as another inverter of the same size. So assume that the load of the NAND gate is also an inverter of this kind. Now, so what we are saying is the ability of this inverter to drive the load. Load is what? Another inverter of the same kind. The ability of this inverter to drive the load should be similar. My NAND gate should have similar ability to drive a similar load. What does it mean? Suppose I have a capacitance here. Now, to pull that capacitance to a low value, what does it depend on? To pull that capacitance to a low value depends on the NMOS current. Now, if I add the same capacitance here and I want to pull it down using this A and B here, I should be able to pull it down in the same time as I pull this particular capacitance down. So we are talking about this NMOS has a certain strength, pull down strength, which means a certain current here. What we are talking about is this series connected NMOS should have the same strength. Together, it should have the same strength as this particular one. In that case, this will be able to pull down that particular capacitance in the same amount of time, because it can provide this current here is the same as the current here. And we are talking about same capacitance connected at the output node here and same capacitance connected. All right. That could be one principle. We are saying we are designing a NAND gate such that it has the same pull down strength and same pull up strength as my inverter. And we can call that NAND gate as a 1x NAND gate. NAND gate of strength 1x. Now, if you want to make a NAND gate of strength 2x, well, you can go ahead and double the sizes here and double the sizes. That will become a NAND gate of size 2x. And you can have 4x and 16x and all that you can make. But 1x could be by building a NAND gate of the same strength as this particular inverter here. So we can start with that particular principle here. Same strength of the NAND gate as the inverter here. All right. Now things are a little bit more complicated. When I look at a NAND gate, there are different ways in which the NAND gate can switch. Now note that this is one possibility. I can have B which is connected to one here. So this is off. This is on, and this is A is what is switching. The input A is switching. It may go from 0 to 1, in which case output will go from 1 to 0, or it may go from 1 to 0, and in which case the output will go from 0 to 1. So this is the input which is switching, A. Or I could have this situation here. I could have A which is connected to 1 and B which is switching. 0 to 1, 1 to 0, and all that. I can have this situation. One can even think of this situation. Let's say maybe both simultaneously switching. Or somebody may even short all the inputs together and say 0 to 1. Or what it also implies is that A and B are simultaneously switching from 0 to 1 and 1 to 0. So I can have these three situations here. I can have a NAND gate working under this condition, NAND gate working under this condition, and a NAND gate working under this condition. So note that with that, now the issue is what happens. PMOS is straightforward. Note that PMOS is, well, both this, as far as PMOS is concerned, both these situations are the same. In this case, this transistor is off, this is switching. In this case, this is off, this is switching. So that's fine. PMOS is not an issue. NMOS is more of an issue. NMOS is series connected transistors. Parallel means it's just off and this is on. So it's straightforward. NMOS is more of a problem. What happens in this case, what happens in this case, and what happens in this case. In each one of these cases, the currents in the NMOSs are different. Okay, so let me show you how the currents change. So look at, I've just taken the NMOSs now. I've removed the PMOS from the top part here. So NMOSs are here, all these are NMOSs. In one case, this is permanently, on with VDD connected. In the other case, this is VDD connected here. And the other case is shorted together. And so these are the three cases which are relevant for NAND gate. And just for the sake of comparison, I'm showing inverters. In inverter, we have single NMOS pull down, single NMOS transistor in the pull down network. All transistors are 4 lambda by 2 lambda. Just for the sake of comparison, so that you can see 4 lambda by 2 lambda, 4 lambda by 2 lambda, 4 lambda, all of them are. All right. So in one case, what I did was I put here 1.65 and 1.65. Why am I interested in 1.65 and 1.65? Note that in a VTC, when I'm looking at voltage transfer characteristics, inverter threshold voltage, I would like to design it as 1.65. So that's why my interest in when input is 1.65 and the output is also 1.65. I want to see what happens to the currents in this case, in this case, in this case. So in this case, the current is 43 microamperes. In this case, the current is 18.35 microamperes. In this case, 31.1. And in this case, 42.76. All right. Let's try and understand why this is so. It's obvious, both transistors are, as I said, all transistors are 4 lambda by 2 lambda. So if I connect two transistors in series, it's sort of obvious that when I connect two transistors in series, the effective resistance will increase, current should drop. So, I don't think anybody should expect that current would be increasing. Current should decrease. The issue is how much should it decrease? Why is it decreasing? Why is it decreasing so much here and not so much here? All right. So look at these two NMOSs connected in series under different conditions. This one, if you look at this case where you take two NMOSs and you connect them in, short them together, and you connect the voltage here. In this case, it can be shown that if you neglect note that the other thing that is happening is body is connected to ground here. So threshold voltage of this transistor is a little bit higher as compared to this particular transistor. If somehow I could make the threshold voltage of this transistor same as threshold voltage of this transistor, We can then show that when you take two NMOSes and you connect them like this here, it can be thought of as a single NMOS, but with half the size. Through equations, one can show that. Two NMOSes connected in series with both their gates tied together and with identical threshold voltage, one can say that the size of these, effectively it behaves like a single NMOS with half the size as this one, which is sort of what you are seeing here. This is 4 lambda by 2 lambda, and we are saying this behaves as if it's a single transistor with half the size. So it behaves like a 2 lambda by 2 lambda. Half the size means current directly scales with this thing, so current is almost decreasing to half. Now it's decreasing more than half because the threshold voltage of this transistor is high, because this is connected to ground. If this were connected, body and source were connected together, this would have come out to be very close to exactly half. Okay, so this we can show by straightforward writing the equation of NMOS here and NMOS here, and rearranging the equation. We can say effectively works like a transistor of half the size when the gates of both the transistors are shorted together. All right, so that's 18.35 that you see here. 43, then you get 18.35. Look at this one. This is easier to understand. This is very close. 42.76 is very close to 43. Now, when I look at these two transistors here, what happens is this behaves in linear region and this behaves in saturation region. Note that the input to this is 3.3. Large input, large gate voltage is applied. This goes into linear region. So if this is 1.65 here, the voltage here, some voltage will drop. The voltage here will come out to be maybe 1.3 or something, depending on the currents and all that will come out here. This transistor is in saturation region. And note that this transistor is also in saturation region. Both are in saturation. This is also in saturation region. This is 1.65, this is 1.65. And when two transistors are in saturation region with the same gate to source voltage, their currents are the same. The small differences come about because of channel length modulation and all that, because of different drain voltage that is here. So there's a small difference here, but first order approximation, the current in this is expected to be the same as current, because effectively the current is decided by this transistor here. It has 1.65, this also has 1.65, both are in saturation region. And so the current here is very close to the current here. The current in this case is half of the current here. The next case is interesting. In this case, this is in saturation and this is linear. I have very high voltage applied here, 3.3. The transistor goes into linear region. And what happens is the voltage here is not ground, obviously, it's a little higher, maybe 0.1, 0.2 or whatever. Now, once it goes high here, this transistor is in saturation. Its effective gate to source voltage is no longer 1.65. Its effective gate to source voltage here is 1.65 minus the voltage here. So let's say 1.3. If the voltage here is 0.3 volt, so 1.65 minus 0.3, you get 1.35. So gate to source voltage is smaller, and therefore the current is smaller. 31.1. Now, how much is it smaller? We have to do some calculation depending on the size here and the size here. We have to do some workout and find out how much is the voltage here, and then calculate what this is. So all these three conditions you can see here. You can compare a single NMOS with two series connected NMOSes under different conditions here. All right. So all these things that you can see here. What happens in this case? This is almost like a single NMOS. This is almost like a single NMOS with half the size. And this one is somewhere in between. 31.1, somewhere in between, which is more complicated, requires calculation. All right. So this is the other one. So this is, remember, 1.65 and 1.65 we are interested in because we are interested in VTC. But when I'm looking at delay, note that when I'm looking at delay, initially the capacitance which is connected here is charged to 3.3, is high. And then I'm discharging that particular capacitance to ground. If I'm taking a NAND gate, and remember this is the lower part of the NAND gate here. Lower part of the NAND gate. And if some capacitance is connected, the capacitance will be discharged by this here, with both of them VDD. So this is more of interest when I'm discharging the capacitor for delay this thing here. So when I applied VDD here, VDD here, VDD here, 546 here, and 235 here, which means two NMOSs connected in series here, with both connected to VDD. The current here is half as much as this. If I put this as 4 lambda and 4 lambda and 4 lambda here. Now, one of the design principles that we were saying is that my NAND gate, these two series connected NAND gates, should have the same strength as my inverter. So if it has to have same strength as the inverter, then these two transistors, I should size them as 8 lambda by 2 lambda, because it's approximately half here, right? So if I put 4 lambda by 4 lambda here, the current would become half, and any capacitor connected here would now take twice as long to discharge, because the current is half. And I want to maintain the same, this strength as this strength here. So I should make these sizes 8 lambda by 2 lambda, 8 lambda by 2 lambda. All right.